Section 1.6, Polynomials and Rational Functions. In this section, we're going to continue our review of some of the topics from college algebra and hopefully see some new applications as well. But for a lot of this, I'll continue to move pretty quickly since we should have seen this material before. But if you find that you're struggling or have extra questions or want to see extra examples, please let me know and we could talk about that in office hours. So in previous sections, we graphed lines and quadratics. In these functions, the x variable is raised to a non-negative integer power. And sort of the blanket term for this type of function is a polynomial function. Okay, so quadratics and linear functions are both examples of polynomial functions. A polynomial function more generally is one in this form down here. So this is a very kind of complicated mathy way of expressing this. But if we look at each of the terms of this polynomial written out here, we have like an a sub n or like an a factor, and then we have the variable factor. Okay, so the a sub n just represents a constant, or we call it a coefficient. So this is just going to be some real number. And then the x to the n, that's going to be our variable x raised to some power n. Okay, and n is going to be a non-negative integer. All right, so some examples of polynomials, like I said, linear functions. So like f of x equals 2x plus 1. That is an example of a polynomial function. Specifically, this is a degree 1 polynomial because the exponent on there is just 1. Another example would be something like this. F of x equals x squared plus 14. This is actually a function from the last example in the previous section that we did. I think this was our demand function. This is a quadratic. So this is, the highest power that we see on the variable x is 2 in this case. So this is a degree 2 polynomial. All right, and then we'll also see higher degree polynomials. So last little example, things like this. X to the fourth minus 3x cubed minus 7x squared plus 1. This is a fourth degree polynomial because the highest power that we see on x is 4. We soon will be comfortable looking at these, evaluating them, and graphing them as well. So here's some just facts about polynomials. The domain of any polynomial function is the set of all real numbers. So all real numbers, all numbers from negative infinity up to positive infinity, if we're writing that in interval notation, as we usually do. All right, and this is just because we don't run into any problems when we're trying to evaluate a polynomial at any real number. Like raising a real number to the first power, second power, third power, like there are no values of x for which that is not possible, assuming that we're pulling numbers from the real numbers. So that's one really nice kind of friendly thing about polynomials, is the domain will always be real numbers, all real numbers. Okay, polynomial functions are classified by their degree. The highest power x in a polynomial is said to be its degree. A polynomial with degree n has a leading coefficient, a sub n, and a sub 0 is what we call the constant term. Okay, so the leading coefficient is just whatever number is being multiplied by x to the highest power. So looking at example 1, let's find x, like the highest exponent that we see on our variable x. It looks like it's this 7 right here. Okay, so this whole thing, 6x plus 7, that's what we call the leading term. So that whole thing is the leading term. Which includes the coefficient and the variable part. And then the leading coefficient is just the 6. This is the leading coefficient. And for this particular polynomial, we are looking at degree 7. Right, because the highest exponent on x is that 7 there. Okay, and then just the kind of basic polynomials that we've already seen. Degree 1 is linear. Degree 2 is quadratic. We were just talking about this. And actually, if we just have f of x equals a sub 0, so just, it equals some real number, this is technically a degree 0 polynomial, and we call this a constant function. And remember, a constant function, the graph of a constant function is just a horizontal line. Okay, and then as we go on, third degree is a cubic function, fourth degree is a quartic, quintic, and I don't say quartic or quintic very often. I'll usually just start saying degree 4, degree 5, and so on. So here are sort of the toolkit polynomial functions, which we call power functions. And these are just polynomials where they have a single term and the leading coefficient is 1. So for n equals 1, f of x equals x, this is just our we could think of it as our parent linear function. If we have degree 2, f of x equals x squared, this is kind of like our parent quadratic function, the parabola. Degree 3, we have this type of shape here. Degree 4, it looks very similar to a parabola, but just a little more flattened out. And, you could do a table of values for any of these functions and, plug in x values and get out f of x values and, plug in numbers like -1, 0, 1, 1/2, -1/2, and look at the output values, and you'll see why the fourth degree polynomial or the fourth degree power function is a little flatter at the bottom than the parabola is. Okay, and then fifth degree power function looks very similar to the third degree one, but just again a little flatter. And we could sort of see this progression as the degree gets higher, it just gets a little flatter at the bottom. But the interesting thing is odd degree polynomials. So these are the odd degree and the even degree. Have very, very similar shapes. Okay, more precisely, the end behavior of the odd degree power functions are all the same. Okay, and the even degree power functions, the end behavior is all the same. So on the odd degree, it's down to the left, up to the right, and even degree, it's up on both sides. Okay, so there's sort of subtle changes in the curvature of these graphs, but the end behavior is the same. That's a very important observation, which will be helpful when we go to graph these later on in this section. Okay, so that's what we're talking about here. So end behavior, this is how the graph behaves for values of x, which are very large in the positive direction or very large in the negative direction. And the notation that we use in calculus, and we're going to be using this a lot, is as x approaches infinity or as x approaches negative infinity. So this is using this little arrow notation. This is just like what's happening as x gets really, really big, what happens as x gets really, really small. We could think of sort of like an infinite table of values where we're plugging in values that get larger and larger and larger in both the positive and negative direction, and we're observing what's happening to the outputs of the function. Okay, and then here's a theorem for polynomials for absolute value of x very large, that is as x goes to positive infinity and as x goes to negative infinity, like we were just discussing. The graph of the polynomial function f of x, here it is, just our general polynomial, is going to resemble the graph of y equals a sub n x to the n. So it's going to resemble the graph of if we just took the leading term and just, defined a polynomial function as being equal to a sub n times x to the n. Okay, so what this means really is it's going to depend on the degree and the leading coefficient. So that's what we're talking about here at the top of page 15. This is the types of end behavior for polynomial functions. So again, just talking about this general polynomial function, a sub n x to the n plus a sub n minus 1 x to the n minus 1, whatever, just a degree n polynomial. The two things that are going to impact the end behavior is whether that leading coefficient, a sub n, is positive or negative. That's the first thing. And the second thing is whether the degree n is even or odd. Okay, because looking down at these pictures, if n is an odd number, meaning that our polynomial has odd degree, remember what the power function looks like is it looks like this, where it goes down to the left and up to the right. So I know that if it has odd degree, it's going to have that kind of behavior. However, remember the power functions, that's all when a sub n is equal to 1. Like the pictures we were looking at above, a sub n is equal to 1 in all those pictures. What if a sub n is a negative number? What that's going to cause is a reflection over the x-axis, and we're going to end up with this type of picture over here. Okay, so the sign, S-I-G-N, the sign of a sub n and the degree of the polynomial are going to be able to tell us what the end behavior is. Okay, so in these second two pictures down here, now suppose that n is an even positive integer. So even degree, looking back up to these pictures, these are the even ones up here. This is where we have end behavior where it's up on the left and up on the right. So we can expect, the left and right branch of the graph of this polynomial to go in the same direction. And again, it goes up and up if a sub n is equal to 1, like it is for those power functions. But what if we have a negative leading coefficient? Then it's just going to reflect over the x-axis again, and then we'll be looking at down and down end behavior. All right, so long story short, if we have odd degree, we're going to have end behavior that goes in opposite directions. If we have even degree, we're going to have end behavior that goes in the same direction. And if it is a negative leading coefficient, it's just going to cause a reflection over the x-axis. So we should be able to determine what the end behavior of a polynomial is just based on this leading coefficient. The leading term, using the leading coefficient and the degree. Okay, so what I want to sort of show you how to do in example 2 is use this arrow notation to communicate what end behavior is. And this arrow notation is going to be we're going to use it constantly, especially in chapter 2 when we start dealing with limits. So in this picture right here, we don't have the full graph of the polynomial. We just have the end behavior is displayed. So it goes down on the left and down on the right. So the way that we write this out, like the way that I express down on the left and down on the right, using sort of proper calculus notation is like this. As x approaches negative infinity, f of x, I'll just write it out and I'll explain to you what it means, approaches negative infinity. So what this is, what I just wrote out, is talking about this left branch right here. So this is saying as x goes to negative infinity, in other words, as we plug in values of x which shoot off to the left, the f of x values, so the y coordinates, are going to go down to negative infinity. Okay, because remember x, this is like horizontal, and f of x, this is like vertical. So as we move horizontally to the left, we're going to see, this graph moving vertically downwards. That's what the negative infinity indicates. Okay, so now if we want to describe what's happening to the right, we say as x approaches infinity, so positive infinity this time, f of x approaches what? What do you think? So as x gets larger, as we plug in large positive x values, what is happening to the y values or the f of x values? Are they going up or are they going down? Are they going to positive infinity or to negative infinity? Well, it's also going down as we look to the right? We're going down on both sides here. So f of x will also be approaching negative infinity as x gets large. All right, so this is the notation that we use to describe end behavior. Hopefully you did this in your college algebra class, but some college algebra classes don't do this, so I figured I'd outline it. One other question, we're not really asked about this, but what can we sort of deduce about the degree and the leading coefficient based on this picture? Well, the degree, is it even or odd? Well, since both sides are going in the same direction, I can tell that this is even. I kind of think of the parabola, right? The end behavior of the parabola, f of x equals x squared. That's where we have both branches going in the same direction. So the degree is even. What do we know about the leading coefficient? Well, since we're going down and down rather than up and up, this is going to be negative. Okay, so just getting a little practice thinking about end behavior. So just a couple other things. Yeah, the gaps between the arrows, so what the actual behavior of the polynomial is in the middle, how are we going to come up with that behavior? So we call this local behavior, and this is going to include turning points in the graph, symmetry, x and y intercepts, and behavior at x intercepts. So we're going to see a whole bunch of different examples of graphs of polynomials, but oftentimes, there will be some kind of end behavior. Maybe it'll go down to the left and up to the right, I don't know. But in between, there are going to be points where we go across the x-axis. There are going to be points where we turn around. There are going to be points where we go through the y-axis. And, we might bounce off the y-axis. There might be another squiggle. There's all kinds of things that can happen in the middle. And most of the work of this section is how do we discover the behavior of any given polynomial. So that's what we're getting into here. Let's talk about relative extrema. So in calculus, a turning point corresponds to a relative or local, these are just two different words for the same thing, extrema, which means a maximum point or a minimum point. So here's the definition of that. A number f of c is a relative maximum for a function f if f of x is less than or equal to f of c for every x in some open interval a to b that contains c. So that's a really sort of convoluted way of just saying, okay, looking at this picture, there's this local maximum right here. I just outlined it. I just, highlighted it in blue. And visually, it's just like we can look at it and be like, oh yeah, that's the highest point in that region there. It's not the highest point of the whole function. We obviously have larger y values over here. But locally, that is the highest point. So if we're looking at some little open interval from a to b, let's say it's from, we could use actual numbers. We could just say from, I don't know, how about -1 to +1? In this open interval right here, this output is larger than the output of any other x value. Okay, so that's all we mean when we say relative maximum. We just mean the highest point of the graph or the largest output of the function in some localized region of the domain. And basically same thing for relative minimum. Same concept, just we're talking about the smallest output of the function rather than the largest one. So this is where we have some number f of c, where f of c is less than or equal to f of x for every x in some open interval a to b. So like we could be looking from +2 to +3 for this example, how about? Right, there's no x value in that little subset of the domain that will give a smaller output value. Okay, so finding relative extrema is super important. Those are very defining features of the graph of a polynomial. Other very defining features of the graph would be the y-intercept. This is pretty easy to find, right? This is always just going to be the ordered pair 0, f of 0. No different than any other function that we've dealt with up to this point. X-intercepts, also very important, a little harder to find, because we have to solve the equation f of x equals 0. So there's going to be some factoring and some work involved in finding x-intercepts. But again, very important to have those points. Those are really sort of critical reference points when we're looking at a graph. Because once you have x-intercepts, if you have a few of those and you have a y-intercept, and you have some information about the end behavior of the graph, you're sort of and maybe you find a maximum point or a minimum point or something like that. Sort of the way we come up with really accurate graphs of polynomial functions is just finding all of these really critical, important ordered pairs that are on the graph, and then we're able to just sort of sketch the graph using those points. Okay, so we want to develop the skills to be able to find all of these important things like end behavior, intercepts, relative extrema. If we can do that, the rest of the job gets pretty easy. Okay, so that was a lot of just discussion of the concepts. Let's actually get into a problem. Example 3, we're given this function f of x equals 0.2 times x minus 2 times x plus 1 times x minus 5. We want to express this polynomial in general form and determine the leading term, degree, end behavior, intercepts, and we want to graph the function as well. So this is a polynomial. I know it doesn't, it's not in that general form of a sub n x to the n plus, down to the constant term. But we can express it in that form by just multiplying it out, and that's exactly what we're going to do down here to get the general form. So I'll just copy down my function. And to multiply this out, we're just going to be foiling, or you could use the box method or distributive property, whatever. There are a few different ways that we can do this. I'll do the box method over here. It seems to be pretty popular amongst students. Let's start by multiplying x plus 1 times x minus 5. So I'll do x plus 1 and x minus 5 up here. Multiplying x and x, I get x squared. This will be negative 5x. This will be x. This will be negative 5. And these, the x, on my highlighter here, the x and the negative 5x are like terms, so I can just add those together when I write down my next step here. So this is going to be equal to 0.2 x minus 2, and now just adding each of those terms together in the box, I'll get x squared, and then minus 5x plus x, that gives me the negative 4x, and then minus 5. Okay, and then for the next step of multiplication, I am actually going to distribute. I'm going to take this x minus 2 and I'm going to distribute it to each of those terms in there. Multiplying a binomial with a trinomial is a little more work. So we'll do that. And it looks like this. X squared times x minus 2 minus 4x times x minus 2 minus 5 times x minus 2. And then I'll just distribute this x squared in, I'll distribute the negative 4x in, I'll distribute the negative 5 in, and I get 0.2 times x to the third minus 2x squared, and so on. And I'm going to check my work here just because I always make mistakes with that, especially the signs. So just looking over my work, making sure everything looks good. Okay, I think we're good. Last step is distribute in that 0.2, add a couple of these like terms together. Those are like terms, those are like terms. So here's what I get. I get f of x is equal to 0.2x cubed minus 1.2x squared plus 0.6x plus 2. And I'll box that up since that is my general form. And I'm happy to have it in general form for the next two things because I want the leading term, I want the degree. The leading term is just this first term in the general form. Okay, so it's going to be the term that has x with the highest power, the highest integer exponent that we see in the whole function. So the leading term is just going to be 0.2 x cubed. So that's the answer for that part. And now for the degree, we again will use that leading term. The degree is just going to be whatever that highest power is. In this case, it's 3. So I'll write the degree of f is equal to 3. That's notation I'll use sometimes just to indicate what the degree of a polynomial function is. And so since the degree is 3, which is an odd number, and I'll also note that the leading coefficient, so what is the leading coefficient in this polynomial? Well, it's just going to be whatever number is multiplying by that x cubed, so it's going to be the 0.2. Since this is positive, it's greater than 0. So these two facts combined, odd degree, positive leading coefficient, means that the end behavior is going to be down on the left, up on the right. Okay, so it's going to kind of resemble the graph of that power function y equals x cubed. Since the leading coefficient is positive, it's not going to be reflected or anything. So I'll write this out as x approaches negative infinity. So as we look to the left of the graph, we'll see that f of x, the output values or the y coordinates on the graph, are going to be approaching negative infinity. All right, so that was just using this arrow notation to describe this behavior. As we go to the left, the graph is going to shoot downwards. And as x goes to positive infinity, so as we look to the right, f of x, the y coordinates, are going to be going towards positive infinity. All right, so that's just using arrow notation to show that we have this behavior in the right-hand branch of the graph. So I will box this up now. Okay. And for intercepts, so we want x and y intercepts. I usually start with y because it's pretty easy. The y-intercept is always just the ordered pair 0, f of 0, which in this case is going to be 0, positive 2. By the way, you could plug 0 into either form. You could plug it into the factored form up here. Just plug in 0 everywhere you see an x and simplify. But what I chose to do is I plugged it into this form because it's a lot easier. If you plug in 0 and raise it to some power and multiply it by some real number, it just goes to 0. So everything, all those terms drop off except for the 2 on the very end. So I didn't have to do any work at all. I could just sort of recognize, I could plug in 0 and I get out 2. So there's my y-intercept. Now for my x-intercept, this is where let's see, I'll write this out. We want the x-intercepts. There could be more than one of these. There probably will be. What we do is we set the function equal to 0, and I would recommend setting the factored form equal to 0. So 0.2 times x minus 2 times x plus 1 times x minus 5. Set that equal to 0 because then I could just use the 0 product property, which says, if we have a bunch of factors being multiplied together and they're all equal to 0, one of them must be 0. So I'm just looking for the values of x that make any of these factors equal to 0. So I'll set x equals 2 equals 0, x plus 1, set that equal to 0, x minus 5, set that equal to 0, and solve for x. So x equals 2, x equals negative 1, x equals positive 5. Okay, so those are the values of x that will make the function equal to 0, and those will give us our x-intercepts. So 2, 0 will be an x-intercept, negative 1, 0 will be an x-intercept, and 5, 0 will give us a third x-intercept. So it's really important that we're able to recognize the relationship between a factor, like x minus 2. So a factor of a polynomial function f is attached to a 0. So a 0 is just the value of x that makes the polynomial 0. So we have that connection. And those are both connected to the x-intercept, which is just kind of the reflection of that 0 in the graph of the function f. So now that I have all this information, I'm going to go ahead and plot these points. I'm going to start graphing it. So I have x-intercepts at 2, negative 1, and at positive 5. I have a y-intercept at positive 2. I know my end behavior is going to go down on the left and up on the right. So already I have a pretty good idea of what this graph is going to look like. I think it's going to be like this type of shape. But that, of course, is not good enough, what I just drew in. We'll want to be a little more precise. I'll do a table of values off to the side just to test a few more values. I'd like to know what's happening at negative 2, positive 1, 3, 4, and 6. And I'm just looking at the graph and, I know what's happening at negative 1, 0, 2, and 5. I'm just sort of picking the integer values around there that aren't actually covered. And I just plugged these into my calculator. I used the trace feature on my calculator. So if you type this function into your calculator, either in factored form or in general form, and hit the trace button after graphing. The trace feature is really nice on your calculator because then you could just type in numbers. Like I'll type in negative 2 into my calculator and it tells me that the output is negative 5.6. We'll put in positive 1 and it tells me the output is 1.6. I'll put in 3 and out comes negative 1.6. And I could just type in any x value and it will tell me the corresponding y value. So rather than doing all the number crunching on your own, I'd really recommend doing that kind of thing. And then I'll just plot each of these points. So -2, -5.6 is around here. And then +1, 1.6 is about there. +3, -1.6, about there. Just go through. And the last one is 6, 5.6. And with all those points on there, I can sketch in the graph. We could also use the maximum minimum function to find where the highest points and lowest points are if we wanted to be really precise and know exactly where the maximum value is. Like right here, or the minimum value right there. But for right now, this is good enough. So that's a good graphing problem. Example 4, what we're doing is kind of working in the opposite direction, where we're given the graph and we're asked to provide some information about the function. So example 4 reads, what can we conclude about the polynomial represented in the graph shown in the figure below based on its intercepts and turning points? So here are a few prompts. Let's see what we can discover or say about the end behavior first. How about? So looking at this graph, I see it's going up to the left and down to the right. So I'll write that out using arrow notation, but we might as well discuss as well, like, what does that kind of end behavior tell us about the degree? What does it tell us about the leading coefficient? Well, since those two arrows are going in opposite directions, that indicates that we have odd degree. I might write that right here. Odd degree. Okay. And it's pointing up to the left and down to the right. So we read graphs from left to right, like we do when we're reading the English language. So I sort of see this as like a decreasing graph overall. So, or thinking about linear functions, it's like negative slope is when it decreases from left to right. So I'm thinking of this as sort of a decreasing function. The leading coefficient is negative. So I might as well write that in too. The leading coefficient is negative in this case. Okay, but the way we write the end behavior using this arrow notation, as x approaches negative infinity, so as we look to the left, f of x is approaching positive infinity, right? It's just going up as we look to the left of the graph. And how about as x approaches positive infinity, what's happening to f of x? Or to the y coordinates on the graph? As we look to the right, they're going down to negative infinity. Okay, so there are the first two things. How about intercepts? X-intercepts, that's going to be the point at which this graph intersects with the x-axis. So I see one here, I see one here, I see one here. Let's approximate what these are. Again, we don't have the actual expression of the function. We just have the graph here to look at. So it looks like we have an x-intercept at -3. This one right here looks pretty close to -1, maybe just a little bit larger, like a little to the right of -1. So maybe -0.8 is what I'll use as the x-coordinate there. And it looks like this one is x-intercept at +2. So I'll write those out. -3, 0, -0.8, 0, and the third x-intercept is at 2, 0. All right, y-coordinate always being 0 because it is just on the x-axis. We don't travel vertically in either direction. Y-intercept, that's this point up here. And that looks like 6. It looks like we're intersecting the y-axis at y equals 6, so y-intercept is going to be the ordered pair 0, 6. And here we have the x-coordinate is 0 because we don't travel horizontally at all to get to that point, just up 6. And now the degree at least. So we know that the degree is odd. We are talking about that. What is the degree though? Like is it 3? Is it 5? Is it 7? Is it 1? Like what is the degree? Like what clues are in this graph that could help us figure out what the degree is? Well, up here in this problem, the x-intercepts each corresponded to a factor in the original expression of the function. And what we'll see, we'll talk about this more later, but the number of x-intercepts, or the number of zeros that we have, including multiplicities, will give us the degree of the function. So the sum of the multiplicities gives us the degree. So looking at this graph down here, I can see, we have 1, 2, 3 x-intercepts. So that means that our degree of the function is going to be at least 3. Okay, and it looks like they cut, the graph cuts straight through these x-intercepts, so I'm inclined to think that it's only a degree 3 polynomial, but at least 3. So the degree of f is greater than or equal to 3. Okay, and that's because of the 3 x-intercepts that we see on the graph. And that's all we're really asked for on this one. Again, just looking at the graph and kind of working in the opposite direction, using those elements of the graph to try and extract some information about the underlying function. Okay, here at the top of page 18, we're going to look at some problems where we're graphing polynomials. That's what we'll do for example 5 and 6, but you'll notice that we don't have any kind of guardrails here, no training wheels, just we're asked to graph the function. So the 3 main things that we'll rely on to get the graphs of these functions are end behavior, which we've talked about, x and y intercepts, which we've talked about, and symmetry, which I want to talk about very quickly just to remind you about even and odd functions. So not to be confused with even degree and odd degree. Here's the definitions for even and odd functions. So I'll say if f of negative x equals f of x, meaning we plug negative x into some function f and all the negatives cancel out and the function is unchanged, then f is even, so it's an even function. And the graphical implication of that is the graph has y-axis symmetry. Okay, meaning whatever the graph looks like to the right of the y-axis is exactly what it's going to look like to the left of the y-axis. And this is a great thing to know about a function. It can cut out a lot of the work. And also just having that property in mind as you're going through the problem, it can help you just kind of check your work and be a little more confident in your answer, or recognize a mistake if you know that it's an even function and you don't see that symmetry. Okay, so that's even. Now, if f of negative x is equal to negative f of x, meaning we plug negative x into the function and it changes the sign of the entire function, or changes the sign of every single term in the function, then f is odd. Okay, it's an odd function, and the implication of that is that the graph has origin symmetry. Okay, and origin symmetry is like if we have, this picture to the right of the y-axis, we're going to have this picture to the left of the y-axis. Like we can obtain the left part of the graph by just rotating 180 degrees around the origin. Or another way to think about it is if you have the whole graph of f and you rotate it around the origin 180 degrees, you'll get the same picture. Okay, so just another type of symmetry that's helpful to know about, helpful to get the graph, and helpful in checking your work, okay, and recognizing mistakes. So let's jump into example 5. Here we are graphing f of x equals x to the third minus 4x. This is a cubic function. So let's jump into it. Let's think about end behavior. And remember, end behavior is determined using the degree. So the degree of f is 3, and the leading coefficient of this function, this is just the coefficient on x with the highest power on it, which in this case is 3. So the leading coefficient here is 1. Okay, and the important things about these two numbers, 3 is an odd number. So we have odd degree, and the leading coefficient 1 is greater than 0. So remember, odd degree means that it's going to be, down on one side, up on the other side. Leading coefficient being positive means it's going to be an increasing function in the long term. So what this tells me is the end behavior is down on the left, up on the right, or using arrow notation, as x approaches negative infinity, f of x will be approaching negative infinity, and as x approaches positive infinity, f of x will be approaching positive infinity. Okay, so down on the left, up on the right. That's good, that's very helpful, just kind of the big picture, what is happening with this cubic function. Let's look at symmetry now. So for symmetry, we just want to look at f of negative x. We'll plug negative x into our function and see what happens. So we have negative x cubed minus 4 times negative x. Be sure to use parentheses like I just did. Okay, and then when we raise a negative to an odd power, the negative survives. So this is the same as negative x cubed and then plus 4x. So this, what we have right here, is it the same as f of x? Well, no, it's not, because it changed the sign of the x cubed. It also changed the sign of the 4x. So it's not even. I can tell now that it is not an even function. What happens if I factor out a negative sign? If I pull out negative 1, I'm left with x cubed minus 4x. Okay, now this is something significant, because inside of the parentheses here, the x cubed minus 4x, that's my original function. So this is equal to negative f of x. So this is significant. This means that this is an odd function. So I'll say odd function. This means that we have origin symmetry. All right, so whatever's happening on this side of the graph, it's going to be reflected around the origin. Okay, so we should have symmetry that looks something like that. Okay, but end behavior and symmetry, these are just sort of broad impressions of this graph. Once we get to intercepts, this is where we're getting into the details. So intercepts, I always start with the y-intercept just because it's easy or easier. It's always the ordered pair 0, f of 0. All right, so this will be the ordered pair 0, 0. That's what I get when I plug 0 into my function. So this y-intercept actually, it's right here at the origin. It's actually an x-intercept as well. So I'm kind of expecting to see, when I solve for my x-intercepts, x equals 0. So might as well do that now. For x-intercepts, we set the function equal to 0 and solve for x, because we're looking for the inputs that make the output 0 in this case. Right, so our x-intercepts are going to have 0 as the y-coordinate rather than the x-coordinate. And I'll solve this by factoring. We have a common factor of x. So pull out an x, and I'm left with x times x squared minus 4 equals 0. X squared minus 4 is a difference of two squares, so it factors to x plus 2 times x minus 2. And setting each of these equal to 0, I get that x is equal to 0. I'll get x equals negative 2. I'll get x equals positive 2. So I have the x-intercepts 0, 0, negative 2, 0, and positive 2. Whoops, I don't need that equals 0 on the end there. Positive 2, 0. Okay, so just to highlight something really important here, remember we have the factors of the polynomial, we have the zeros of the polynomial, so the values that we get from solving, and then we have the intercepts that come from those zeros, the x-intercepts. Okay, really important to understand and highlight the connection between the factors, the zeros, and the intercepts. This is like a big, kind of critical, important thing that we learn in pre-calculus. Important kind of concept relating to functions and graphs. So I've got a bunch of information now. I have my x-intercepts, I've got my y-intercepts, I know I have origin symmetry, I have my end behavior. So let's start graphing this. Since my x-intercepts are relatively small numbers, I'm going to set my scale like this. Every 2 boxes is going to give me 1 unit. Like this. And I'm going to do that in the x and y direction, just to enlarge my graph a little bit. And I will jump in and put down my x-intercepts and my y-intercept. So there they are. And from here, I think it would be good to make a little table of values. The last step for me is pretty much always making a table of values. Okay, and we can do this using our graphing calculator if we want to, using the trace function, as I've mentioned before. That can be a really effective way to do this without using up too much time, which is definitely in your best interest, especially if you're working on a test or a quiz. You want to be very efficient with your time. So using the trace feature again, love the trace feature. I'll put in a few x values. I think, how about -3, -1, +1, +3. I think that would be a pretty good set of numbers to check. Put in -3, I get -15. Put in -1, I get +3. Put in +1, I get -3. Put in +3, I get +15. And I hope that you're seeing the symmetry that we were expecting kind of showing up here. Okay, if I was really, aware of the fact that I have origin symmetry, really I could have just tested, -3 and -1. and I would have known what was happening outside of there. But let's plot these points. So -3, -15, basically it just gets really small, shoots down like that. -1, +3, I have that ordered pair up there. +1, -3, and then +15 way up there somewhere. So I'm just going to sketch this in now. And that is a really nice looking graph. Okay, so end behavior, symmetry, intercepts, and table of values. We can also use our graphing calculator to find the absolute maxima and minima. That is definitely something that we can do if you want to be a little more precise, but for now, I'm just kind of covering the basics, so this is good enough for our purposes today. Let's try another one. Example 6. We want to graph this 4th degree polynomial, so we're getting up there, pretty high degree here. Let's have a crack at it. Let's start with end behavior. So the end behavior, call it EB, because I'm getting lazy. The end behavior, the degree is equal to 4. The leading coefficient is equal to +1 again. So that tells me the end behavior is going to be either up and up or down and down, but since we have a positive leading coefficient, it's going to be up and up. Okay, so even degree, I always think of like the parabola, like it's either going to be like an upward facing parabola or a downward facing parabola, depending on the leading coefficient. Okay, so we'll have an upward kind of parabolic graph here. Okay, so on the ends, I know it's going to be up on the left and up on the right. And we'll have to do some investigating to figure out what happens in the middle. How about symmetry? Are we going to have any symmetry for this function here? Well, let's look at y of -x. So I'll plug -x into the function, and I get -x to the 4th, like that, -5 times -x squared. Remember to include the negative inside of the parentheses. And something interesting happens. These are both even powers, so if you raise it to an even power, the negative sign goes away, so x to the 4th minus 5x squared plus 4. Look at that, that's the same as the original function. All the negatives just kind of disappeared because they were raised to even powers. So this is really good news. The function is even. So I'll say this is an even function. So that means we have y-axis symmetry. This is my favorite kind of symmetry. I feel like it's really easy. You can just, get the right half of the graph and just reflect each of those points to get the left half. So now let's get to the trickier part. Let's find the intercepts. Y-intercept. The y-intercept is going to be the ordered pair 0, f of 0. Or I'm just writing y of 0 for this problem because this function was given in the form y equals this and that. So y of 0, this is going to be equal to 0, +4. Okay, easy enough. Let's find x-intercepts now. X-intercepts, I'll set this function equal to 0 and solve it. So this might kind of scare you because it's 4th degree polynomial. We don't have a quadratic formula for 4th degree polynomial. So we have to factor this. Now we could try to use the rational zeros theorem and synthetic division and guess zeros and all that stuff, but this function is actually quadratic in form. It's quadratic in form, I can tell, because this is there's three terms, it's a trinomial, and it looks kind of quadratic. And it is quadratic in a sense because notice that the exponent on the first term is double. So it's 2 times the value of the exponent of the middle term. This is what indicates that it's quadratic in form. So let's do a little u substitution. We're going to let u equal x squared, just the variable part of the middle term. So then u squared is equal to x squared squared, which is x to the 4th. And this is a great little trick because I can replace x to the 4th with u squared and x with u. All right, we'll substitute back into x in a minute, but for now, in terms of u, this is just a quadratic function. And one that might factor nicely, because two numbers that multiply to 4 and add to -5 would be -4 and -1. So this factors to u minus 4 times u minus 1. And that equals 0. Pretty good. So we could at this point say, u is equal to +4, u is equal to +1. But what is u really? U is x squared. So really it's x squared is equal to 4, x squared is equal to 1. So you could solve by taking square roots. X is equal to plus or minus 2, x is equal to plus or minus 1. So those are the zeros. So our x-intercepts are, we actually have 4 of them. It's -2, 0, +2, 0, -1, 0, +1, 0. So really we got super lucky with this function, it being quadratic in form and having these really nice integer solutions. But yeah, this process, this is called a u substitution. If you haven't seen it in a while, it's a really good trick to have on hand, and we'll use this a lot in calculus later on in this semester when we get to integration. So good to have a little exposure to it now. So we want to graph this. I'm going to set my scale in the same way that I did before for the last example. Every 2 squares is going to be 1 unit, just to enlarge the graph a little bit, or shrink the viewing window, however you want to look at it. But I think the graph should fit just fine if we do this. And I can plot my x-intercepts, which I know are at +1, -1, +2, -2. I have a y-intercept at +4. Okay. And from here, I think it would be good to do a table of values. So again, you are welcome to use your calculator and the trace features to save yourself a little time. That's what I do. So a little table of values to finish it off. So what would be some good values to test? Well, I'm just testing values in the sort of region of the graph where I don't know what's going on. So maybe like, looking at the right hand side, I'd like to know what's happening at +3. Maybe between 1 and 2, so like 3/2, maybe 1/2 as well. And since I know that I have y-axis symmetry, I'm not going to test any values to the left of the y-axis. I'm just going to reflect the points over once I get these 3 ordered pairs. So Let me do it. I put in 3 and I get out 40. I put in 3 over 2 or 1.5, same thing, and I get negative 2.1875. And I put in 1/2 and I got out 2.8125. Okay, so let me plot those in there. So 1/2, 2.8 something something, so around here. Put in 3 over 2 and I got negative 2.1 something, so around here. And then 3, I'm all the way up at 40, so just gets, you know, really large, really fast over there. So the right branch looks something like this. Now, I'm just going to reflect each of those ordered pairs that I just found over on the other side of the y-axis, because I know that I have y-axis symmetry because this is an even function, and I'm just going to sketch in the curve like that. So there it is. There is my graph. Okay, you could totally go in and find those local maxima and local minima if you want to be super precise about it. We're going to use derivatives to do that in a couple chapters. But there it is. This is definitely good enough for sort of pre-calculus expectations. All right, so next up, moving into rational functions, let's have a look. So the definition here, a rational function is a function in the form y equals f of x, where f of x is equal to p of x over q of x, where p of x and q of x are both polynomial functions. So a rational function is a polynomial divided by a polynomial. The domain of any rational function will be all real numbers except for those which make the denominator 0. Makes sense. We don't want to divide by 0. So, you know, some basic examples of rational functions. The parent function, the most simple basic rational function, is y equals 1 over x. Okay. 1 is a polynomial. It's just the constant polynomial function. X is like a linear function, y equals x. That is a degree 1 polynomial. Okay, but we could have things that are a little more complicated, like y equals x squared minus 1 over x squared plus 2x plus 1. That is also a rational function, right? It's a polynomial divided by a polynomial. So we'll see a whole bunch of different variations and examples of these, and our main goal is to be able to graph them. So graphs of rational functions, when graphing rational functions, we pay attention to intercepts, symmetry, transformations. We also look at things like the domain of f, so finding the zeros of the denominator, finding the degrees of the numerator and denominator will help us get some information about asymptotes, so horizontal asymptotes. Okay, and we also have vertical asymptotes. Those are going to relate to the zeros of the denominator. So let's jump into some examples. Just a simple one to start out with, and then we'll talk about asymptotes in a little more detail. But example 7, we want to graph f of x equals 1 over x minus 2. Okay, so first of all, the parent function of this, and I'll just call it p of x is equal to 1 over x. That is the parent function, okay? And what this graph looks like is, just to plot it down here on the grid. I'm going to enlarge the graph again in the way I did for the last couple examples, just because I like to be able to, view all the details a little more clearly. So same scale. Okay, so that's 1, 2, 3, 4, and so on the x and y axis. The parent function looks like this. We have a vertical asymptote at the y-axis. We have a horizontal asymptote at the x-axis. And this is one of our toolkit functions, one of those functions that we should have kind of memorized. But if you don't, you could always do a table of values to jog your memory. Doing a table of values for p of x, p of x, you put in 1, you get out 1, you put in 2, it's 1 over 2, put in 3, it's 1 over 3. Put in 1/2, and 1 divided by 1/2 is 2. So anyway, just if you are not familiar with this graph or want to understand it better, table of values, that's the best way to get to know a function. Okay, but the reason I'm talking about the parent function here is because f of x is just equal to p of x minus 2. Notice that instead of x, I just have x minus 2. So what this tells me is I can obtain the graph of f by shifting, by a transformation of the parent function p. Okay, so I'll write, I'll say since f of x is equal to p of x minus 2, we can obtain the graph of f by shifting the graph of p two units to the right I can't remember if I said left a second ago. Yeah, we shift 2 units to the right. If it's x minus 2, it's kind of the opposite of what you would think if it's inside of the function. We're shifting to the right by 2 units. Okay. Another way to think about this is, f of x is equal to 1 over x minus 2. The denominator can't be 0, right? So if we were to find the domain of f, we would set the denominator equal to 0 and solve. So if we set x minus 2 equal to 0, we see x equals 2. That is going to be a vertical asymptote. Okay, so the domain of f will be all real numbers except for 2. So negative infinity up to 2 union 2 to positive infinity, using the parentheses there to skip over that value. So anyway, just another way to sort of notice that we're going to have a shift to the right by 2 units. So here is the graph of f. I'm just going to take that graph that I just drew of the parent function p, and I'm going to shift it over to the right. So I could mark out, I'm going to have a vertical asymptote at x equals 2 now, because that is not in the domain. Horizontal asymptote will remain unchanged. It'll still be the x-axis. And I'm just shifting all those ordered pairs that I had from the parent function over by 2 units. And we get a graph that looks something like this. Okay, so just trying to jog your memory on rational functions, and this is just an example coming from the parent function. Okay, so those asymptotes, the vertical one, if we plug values of x that are really close to 2, we're going to get a denominator which is very, very small, which makes the output very, very large. That's why we have the graph going up towards positive infinity and negative infinity on the left on the right and left, respectively. And as we plug in values of x that are very, very large into this function, like if we look at f of 100, that's going to be 1 over 100 minus 2, which is 1 over 98. That's a very small number, right? So as we look off to the right or to the left, we're going to see values of x getting very, very close to 0. So that's how we approach that horizontal asymptote. And that's what we're talking about down here. So for vertical asymptotes, that's kind of what we're talking about first here. To indicate that x is approaching a number a, we use arrow notation. It's also important to indicate whether it's approaching from the left or from the right, right? Because like on this graph up here, as x approached 2 from the right-hand side, that's like this branch of the graph, we see the values of x were going up to positive infinity. But if we approach 2 from the left-hand side, the values of x are going down to negative infinity. So, this notation x approaches 2 is not really descriptive enough. We have to specify whether it's from the left or from the right. So that's what this notation is down here. If x is approaching a with this little negative sign up here in the exponent's place, that means x is approaching a from the left. And a little plus sign indicates we're approaching from the right. And if we don't have a minus sign or a plus sign, that means x is approaching from the left and right. Okay, so from 2 sides. All right, and then as x is approaching negative infinity, means x becomes unbounded in the negative direction. And x approaches positive infinity means x becomes unbounded in the positive direction. All right, and the way that we define, what is a vertical asymptote, the line x equals a is a vertical asymptote if the graph of f of x, is an asymptote of the graph of f of x if any of these conditions hold. Basically, if f of x is going to negative infinity or positive infinity as x approaches a from the left or from the right, or both. Okay. In other words, if the y values are approaching positive or negative infinity near x equals a, that means we have a vertical asymptote at x equals a. Okay, and at that asymptote, the function will be discontinuous, meaning we couldn't draw the curve without picking up our pen. There is a break in the graph. And we call this an infinite break. All right, so we'll see this in examples very shortly. Let's talk about horizontal asymptotes. So I kind of alluded to this in that last example. The line y equals c is a horizontal asymptote of the graph of f of x if any of these conditions hold. If f of x approaches c as x approaches negative infinity, or if f of x approaches c as x approaches positive infinity. So this is like as x gets really, really big, if we're looking at a graph, and let's say here is c on the y-axis. If as x gets really, really big, it approaches c. It gets closer and closer to that. The outputs of the function get closer and closer to c. This is what we're talking about when we say horizontal asymptote. So it's like we have this dotted line here that the graph gets closer and closer to, but never quite touches. Rational functions will have at most one horizontal asymptote. If we had more than one, it would, it kind of contradicts having a function where it passes the vertical line test. So we'll just see one horizontal asymptote at the most. Okay, so finding vertical asymptotes, we just set the denominator equal to 0 and solve any solutions. X equals a will be vertical asymptotes as long as p and q, the numerator and denominator, have no common factors. So let's look at some examples here. I'm throwing a whole bunch of conceptual stuff at you. Let's look at example 8. This will help out a lot. So if we want to find the vertical asymptotes for this function f of x, really what we're doing is we are factoring. So factoring the numerator and denominator is usually the first thing I do when I see a rational function. And for this function, the numerator is just a linear factor, so that's not going to factor at all. The denominator is a difference of two squares. This factors pretty easily to x plus 3 times x minus 3. So before I say that I have vertical asymptotes at positive 3 and negative 3, I have to make sure, are there any common factors between the numerator and denominator of this rational function? Or is there any cancellation that happens? No, there is not in this case. Okay? So, neither of those factors in the denominator are going to go away. So really, I can just set the denominator equal to 0 and solve. Set denominator equal to 0 and solve for x. Okay, so x plus 3 times x minus 3 is equal to 0, leaving it in factored form because that just shows me that x is equal to negative 3 and x is equal to positive 3 are the two solutions to this. So that means that I have these two vertical asymptotes. So vertical asymptotes at x equals negative 3 and x equals positive 3. And I'm also going to point out that the domain of f will be all real numbers except for those two values. So in interval notation, we write this negative infinity to negative 3, union negative 3 to positive 3, union positive 3 to infinity, right? Because the domain, if we're just looking at a number line, it's all real numbers except for negative 3 and positive 3. Right? So like if I was going to write the set, it's like all the numbers to the left of negative 3 jumping over that value, and then up to positive 3 again jumping that value. So open bubbles at negative 3 and positive 3. So the way that we represent that is like, okay, we've got this set to the left of negative 3, and then the set between negative 3 and positive 3, we want to include all those values. And then all those values to the right of positive 3, but just jumping over negative 3 and positive 3. Okay, so we weren't asked for any of this, but it's very important to be able to express your domain, and with rational functions we can get these kind of interesting looking domains. We want to be able to represent them in interval notation. Okay. So in general, I just want to write this up here. To find vertical asymptotes, we want to simplify f of x, right? Make sure we have no common factors between p and q. And then we want to set q of x equal to 0, set the denominator equal to 0, and solve for x. Okay, and that's what we did in example 8. And for example 8, you could put it into your graphing calculator if you're curious about what the graph looks like, but what it looks like is it's like this. I'm just going to sketch, very crude kind of sketch here. But we do in fact have these vertical asymptotes at -3 and +3. The graph looks something like this. These rational functions have super cool graphs. I really like them. The graph looks something like that. Okay, so you'll see that we have the vertical asymptotes at -3 and +3. So you can always use your graphing calculator to kind of check your work on a problem like this. Okay, so horizontal asymptotes is what we'll talk about next. So remember, a rational function is just a polynomial function divided by a polynomial function. Okay, and it turns out that we can use the degrees of the numerator and the denominator, so of p of x and q of x, to determine what the end behavior is, or what the horizontal asymptotes of rational functions are. Okay, so we'll be looking at the degree of the numerator versus the denominator. And remember, the degree we can determine by just looking at the leading terms of each of those functions. So here are the rules down here. So finding horizontal asymptotes, if the degree of p is equal to the degree of q, so numerator and denominator have the same degree, then the ratio of the leading coefficients, so a sub n over b sub n, so looking up here again, leading coefficients of each of those polynomials, that will give you the horizontal asymptote. Okay, if the degree of p is less than the degree of q, then horizontal asymptote is just y equals 0. And if the degree of p is greater than the degree of q, then there is no horizontal asymptote. So looking at example 9, let's find the horizontal asymptotes for each of these. So for this first one, again, the important thing is degree of p versus degree of q. So in this case, they're both quadratics. Okay, numerator and denominator are both quadratic, so that means that they're both degree 2. So I'll just make a note that the degree of p, the numerator, is equal to the degree of q. And this is the case where the horizontal asymptote is the ratio of the leading coefficients. So the horizontal asymptote is going to be y equals the leading coefficient of p. So what is the leading coefficient of p? I'm just looking at the numerator. What is the coefficient on x squared? It's just 1. And what is the leading coefficient of q? It's just 2. All right, so our horizontal asymptote is going to be the line y equals 1/2. All right, and you can totally verify this by using your graphing calculator, typing in the function and graphing it, and what you should see is the graph converging to this horizontal line, y equals 1/2. All right, and that's what you will see. For the second function, again, looking at the degree, so it looks like numerator is degree 3, the denominator is degree 4. So for this one, the degree of p is less than the degree of q, the denominator. So this is kind of the easy case. For this one, the horizontal asymptote is just going to be equal to 0. So it's going to be the line y equals 0. In other words, the x-axis. Notice that that was the case for this first example, the first graphing problem we did up here. Example 7, the degree of the numerator, the degree of p was equal to 0, and the degree of q was equal to 1. So the degree of p was less than q. That's why we had y equals 0 was the horizontal asymptote. Okay, and that's what's happening with this second function here. The third one, I see that the degree of p is greater than the degree of q because degree of p is 4, degree of q is 1. So in this case, we have no horizontal asymptote. All right, now let's have a look at example 10, where we want to find the intercepts, asymptotes, and we want to graph this rational function right here, f of x, which is equal to x squared minus 5x over x squared minus 4. So we have a quadratic in the numerator, quadratic in the denominator. Let's just jump in and start finding some intercepts. And I like to start with the y-intercept, just because it's easy, gives me a little forward momentum. This is always, for any function, the ordered pair 0, f of 0. So what happens if we plug 0 into this function f? I end up with 0 over negative 4. That's what I get if I evaluate this function at 0. And any fraction that has a numerator of 0 is just equal to 0. So the origin 0, 0 is going to be our y-intercept. Okay, cool. Let's find x-intercepts now. Now for x-intercepts, normally what we do for any function is we set the function equal to 0 and solve, because we're looking for the values of x which make the function equal to 0. But since we're looking at a rational function here, like what makes a fraction equal to 0? Well, we just saw this when we were finding the y-intercept. If the numerator of the fraction is equal to 0, then that means that the whole entire fraction is equal to 0. So a nice shortcut, just to spare ourselves a little work, if we're trying to find x-intercepts of a rational function, we just set the numerator equal to 0. Okay, we can set the numerator equal to 0 because any values of x which make that numerator 0 will make the whole function f equal to 0. So I'll set this equal to 0 and solve. Solving by factoring is going to be the move here. So I factor the left-hand side just by pulling out that common factor of x, and then I can, set each of those factors equal to 0, and I get that x equals 0 or x equals 5. So our two x-intercepts are going to be 0, 0. I was kind of expecting to see that because that was our y-intercept. So our y-intercept is the same as the x-intercept. Just goes through the origin. And then we have 5, 0. All right, pretty good. I'll just highlight these. I'm going to need them in a moment when I go to graph. Now, after intercepts, we want to see if we can figure out what the asymptotes are. So let's do asymptotes now. How about we start with vertical asymptotes? Vertical asymptotes, these are going to occur wherever we have zeros of the denominator, which do not cancel with a zero in the numerator. So when I'm going to find vertical asymptotes, I usually start by rewriting the function in fully factored form just to ensure that I don't have any common factors. So I could rewrite f of x as, so the numerator is x times x minus 5, and the denominator factors, it's a difference of two squares, it factors to x minus 2 times x plus 2. All right, so now that I see that we don't have any common factors between the numerator and denominator, there are no cancellations that can happen here, I know that the two factors in the denominator are going to be associated with my vertical asymptotes. But really the way that we solve for vertical asymptotes is we set the denominator equal to 0 and solve. Okay, so normally it would look like this, but I would just solve this by factoring anyway. So I'm going to do the x minus 2 times x plus 2. So I get these two solutions, x equals positive 2, x equals negative 2. And now these two little equations are actually the equations to my vertical asymptote. So let me highlight these. So the line x equals 2 is just the vertical line going through x equals 2 on the x-axis. And x equals negative 2 is the vertical line at x equals negative 2. Okay, so that concludes vertical asymptotes. Now we just got to find horizontal asymptotes. Really, I should say horizontal asymptote, because there can only be one at most. In some cases, there isn't a horizontal asymptote at all. So in this case, for this function, remember we said the numerator and denominator are both quadratics. So the degree of p, that's the numerator, is equal to the degree of q, the denominator. And in this case, the horizontal asymptote is just the ratio of the leading coefficients. And what are the leading coefficients here? Just 1 and 1. So the horizontal asymptote will be the line, so here I'll just put a little note here. Ratio of leading coefficients. It's going to be the line y equals 1 over 1, because those are the two leading coefficients. I could just simplify that to the line y equals 1. This is a horizontal line, which just intersects the y-axis at the line y equals 1, or at that ordered pair 0, 1. Now I have a lot of good information on this function here. I think I'm ready to start plotting points, and I'll draw in these asymptotes, and then we can use a table of values to fill in any gaps that are left. So I'll start by putting down the points. I only have 2 points. I have, this graph goes through the origin, that's both the y-intercept and one of the x-intercepts, and I have a second x-intercept at 5, 0. And now, how about in red, I'll do my asymptotes. I have a vertical asymptote at negative 2. That's the line x equals negative 2. So a little dotted line there. I have another vertical asymptote at the line x equals positive 2. And I have a horizontal asymptote at the line y equals 1. All right, so that's the line y equals 1. This was x equals negative 2. This is x equals positive 2. Okay, this is definitely not enough information to get this graph. I need to know quite a few more ordered pairs. But now that I have all these asymptotes drawn in, I can sort of envision what the behavior is going to be like, because remember, the graph is just going to be getting closer and closer to these asymptotes as we approach them. So let's do a table of values to finish this thing off. Do some inputs and some outputs. And for this, I'm going to use the trace feature on my graphing calculator. So I'll type this function into my graphing calculator and choose some inputs, and it'll spit out the outputs for me really quickly. This is totally allowed. You can do this on homework, on tests, since we'll have our graphing calculators for exams. So it's really worthwhile knowing how to use it. But I need to select, like, what are some good x values to plug in? Well, I only know what's happening at 0 and 5, so pretty much anything other than 0, 5, and also I don't want to plug in -2 or +2 because I know the function is not defined at those values. But, you know, like +1 would be good, 3 would be good, 4 would be good, just to figure out what's happening in this region over here. Looking to the left, I might want to put in -1, maybe -3, -4. That would be good. There are a few more values I would like to plug in. I want to know what's happening close to the vertical asymptote. So, you know, like focusing on this vertical asymptote at x equals -2, like I want to know, is it going up to positive infinity like that at x equals -2, or is it going down to negative infinity? So the way that I can figure that out is just plugging in an x value which is really close to -2 but on the left. Like I could plug in -2.1. That's 2.1. I can do the same thing on the right. I could put in -1.9. All right, depending on if I get really big values or really small values there, that will help me determine, you know, what the behavior is near that asymptote. And I'll do the same thing for that other vertical asymptote at x equals 2. I'll plug in +2.1 and +1.9. Okay, so again, using my graphing calculator, I put in 1, I got 1.333 repeating, so 1 1/3. I put in 3, I got -1.2, -0.333. That's what I got for plugging in 4. Write the rest of these in. So I put in -1.9 and got out -33. So that tells me that close to this vertical asymptote right here, what the graph is going to be doing is it's going to be going down, right? -33 is a large negative number. All right, and then I put in +1.9, I got 15. That indicates that as I approach this vertical asymptote at x equals 2 from the right, it's going to be going up, right? Because I got a pretty large positive number. Okay, so that's what I mean when I say, like, you know, determine the behavior near the asymptotes by picking values to put into your table of values, which is very close, x values which are very close to those vertical asymptotes. Okay, I'm going to plot a couple ordered pairs here, 1 1/3. You can, at your own pace, plug in some values that you got. Okay, there are those values. if you put in negative 2.1, you get out a big number, so the graph is going up like that. If you put in positive 2.1, you get a very small number, indicating that the behavior near that asymptote goes down like that. And you could plug in more ordered pairs if you like, but I've got a pretty good idea of what this graph is doing now. And what it looks like is kind of your standard hyperbola. You know, like it looks similar to the graph of y equals 1 over x. But we have this branch in the middle that has emerged, which is interesting. Looks like kind of like a cubic function almost, that branch in the middle. But to the left and to the right, it looks like pretty standard hyperbolic behavior. And we see that the graph, as we look really far to the right, so talking about end behavior, as we go really far to the right, we see the graph is approaching that horizontal asymptote, y equals 1. If we look really far to the left, we see the same thing, except the graph is approaching it from above. And I get asked about this sometimes. Right here, like this part where the graph crosses that horizontal asymptote. And, you know, because you think, like, aren't asymptotes these lines that you never cross? You can cross a horizontal asymptote, and it will happen sometimes, and it happens in this case. Vertical asymptotes are the ones that we really, really cannot ever cross because those x values are not in the domain of the function, so you'll never see us cross a vertical asymptote. But horizontal asymptotes, this happens all the time where we cross over it at a point like that one there. But at this point, that's a really good graph, you know, given that we did this by hand, just using our graphing calculator for the trace function for a little help with that computational stuff. This looks really good. We were able to get this by just getting the intercepts, vertical and horizontal asymptotes, and using our graphing calculator to fill in the rest. Let's do another one, example 11, same instructions here. We want to find the intercepts and asymptotes, and we want to graph. So for this function in the numerator, we have x squared minus 3x minus 4. In the denominator, we have 4x squared minus 12x plus 9. Oftentimes, I'll start by just factoring the numerator and denominator, like first thing, because I know that that'll make it easier to find my zeros and my vertical asymptotes. So how do we factor the numerator? What are two numbers that multiply to negative 4, add to negative 3? I think that negative 4 and positive 1 will do it. So this factors to x minus 4 times x plus 1. That's good. How do we factor this denominator? The leading coefficient for this is not equal to 1, so I'm going to have to split the middle term. And you can do this off to the side. You know, I'm going to erase this in a second. But if you want the practice factoring, okay, the number in the top is going to be a times c, so 4 times 9, which is 36. And in the bottom, we'll put negative 12. So which two numbers multiply to 36, positive 36, and add to negative 12? I think negative 6 and negative 6 will do that. So I'm going to split the middle term, and this is just what we have to do when the leading coefficient is not equal to 1. Okay, so there I split that negative 12x, and I'll factor by grouping. So 4x squared minus 6x, plus sign in the middle, negative 6x plus 9. Pull out a common factor of 2x. I'll get x minus 2, or sorry, x minus 3, 2x minus 3. Here I'll pull out a negative 3 is the greatest common factor, and I'll get 2x minus 3. Okay, so this is good. 2x minus 3, those are matching right there, so I can pull that out as a common factor. 2x minus 3 times 2x minus 3. We could even write this as 2x minus 3 squared. So that's what I'll write up here. 2x minus 3 squared. So I'm going to take this out and clear up some space. So now I can actually get into it, and this problem's going to be pretty, we just did a lot of the hard work just getting the factored form of the numerator and denominator. But let's jump into getting intercepts. And I'll do the y-intercept. It's the ordered pair 0, f of 0. And if I put 0 into this function, I'll get negative 4 over 9 as the y coordinate. So there's that. Now for x-intercepts, I'll set the numerator equal to 0. And this, we already factored it, x minus 4 times x plus 1. So my solutions are x equals positive 4 and x equals negative 1. So my two x-intercepts are 4, 0 and negative 1, 0. So I'll highlight those. So there are my intercepts. Let's find asymptotes. And I'll start with my vertical asymptotes. And I could find these by just setting my denominator equal to 0. So I'm just going to set the factored form 2x minus 3 squared, set that equal to 0. And solve, I can take the square root of both sides to deal with that second power. 2x minus 3 equal to 0, and I'll just solve for x. Add 3 to both sides and then divide by 2, so I have a vertical asymptote at the line x equals 3 over 2. Okay, not too bad. Horizontal asymptote. Let's find a horizontal asymptote. I think I might do that over here. So horizontal asymptote, we have to look at the function and see how the degree of the numerator and denominator compare. In this case, they're both quadratic again. So the degree of the numerator p is equal to the degree of the denominator q. So that means that we are going to have ratio of leading coefficients. So y equals ratio of the leading coefficients. Leading coefficient of p is 1. Leading coefficient of q is 4. So that's it. Our horizontal asymptote is going to be the line y equals 1/4. Now, a lot of these numbers are smaller. And having that 1/4, like I'm just thinking, how do I want to set the scale on my graph so that, the entire picture is clear and we can clearly observe all of the key features of the graph. I think I might set my scale like this. Instead of counting by 1, I'll be counting by 1/2. So this will be 1, 2, 3, 4. So I'm enlarging my graph. And I'll do that on the X and on the Y. All right. And I can start putting in some of my sort of key features of the graph, like I can put in my y-intercept at 0, -4/9. So 0, -4/9, that's going to be a little less than 1/2. I have x-intercepts at -1 and 4. All right, and then I have asymptotes here. So vertical asymptote, I just have the 1 at 3/2. So that's 1.5. So I'll put a dotted line there. And let's also do our horizontal asymptote. That was at 1/4. Right, so since each little square there represents a half of a unit, I put 1/4 just right there. Okay, and now I just want to put this into my graphing calculator so that I can use the trace feature and really quickly generate a few more ordered pairs to help myself out, get the rest of the graph. So putting this into my graphing calculator and using the trace feature, and let me select some good x values to plug in as well. So I'm just going to do this down here. So inputs and outputs. So kind of same thing as before, like I'm just choosing input values in regions of the graph where I don't have a lot of information, paying extra close attention to values that are close to the asymptote or the vertical asymptote. So this is the line x equals 3/2 or x equals 1.5 is another way I could write that. So good input values would be like, okay, 1, 2, 3, maybe -2, and then a couple values that are close to the vertical asymptote. How about 1.4 and 1.6? Sure. Okay, putting in 1. Again, I'm using my calculator, the trace feature. I put in 1, I get out -6. I put in 2, I also get -6. Put in 3, I get -0.444. I put in -2 and I get 0.1224, just rounding it to that decimal place. Let's put in 1.4, I get -156. Wow, okay. I put in 1.6 and I get out -156. I'm noticing some kind of cool symmetry here with respect to that vertical asymptote. So let's plot these points. 1, -6, that is a little off the graph, it's just right there. 2, -6. I have 3, -0.44, so right about there. What else do I have? -2, just a little bit above the x-axis. Okay, and then obviously it goes down to negative infinity to the left and to the right of that vertical asymptote. So my graph looks something like this. I'm going to sketch it in. We can see it pretty clearly approaching that horizontal asymptote as well. And there we have it. There is the graph of our function. Remember the original function, f of x equal to x squared minus 3x minus 4. Minus 4 over 4x squared minus 12x plus 9. So no middle branch in this case, but very interesting graph nonetheless. And that's going to conclude section 1.6 on polynomials and rational functions. This is a big section, obviously. But this should be review for the most part, but I hope that this was useful, just getting a bit of practice, working with polynomials, rational functions, some extra practice and reminders relating to graphing, factoring, all these important kind of essential skills, which we should have obtained in our pre-calculus training. Next up, we're going to talk about exponential functions, and beyond that, logarithmic functions, so we will get to that in section 1.7. I'll see you in that next video.